Welcome to example 6. We have a problem that instead of having an air wedge, we have a grease wedge. So basically we have a plastic piece here, and then below this is a piece of flint glass, and then wedged in between here is some silicone grease. And we're asked to figure out, first of all, at this line of contact, to this point of contact here, whether we're going to see it start with a bright fringe or start with a dark fringe. And then secondly, I would like to know how closely spaced these fringes that we'll see in here. So let's first start off again looking at the two reflections that occur at the top interface, say here, and the bottom interface here at B, and discuss whether there are phase shifts or not. So at point A, hopefully you'll see you are going from an index refraction of N1, which is 1.4, that's plastic, going to an index refraction of N2, which is grease, of 1.5. So you're going from less dense to more dense. Therefore, you will go through a 180-degree phase shift. Then, if you look at point B, or at the reflection that is occurring at the lower surface here, we're going from N2, which is 1.5, to now flint glass, which is an index refraction of 1.6. And so once again, you're going from less dense to more dense, and there is a 180-degree phase shift. Therefore, or thus, we have a no net phase inversion. There is no net phase inversion or difference between them. So this means that if you were to bring points A and B closer and closer and closer to the point of contact, that when they leave and T is essentially 0, then they are going to be in sync with one another. They're going to be crest to crest and trough to trough, so therefore we will have constructive interference at the contact point. Thus, we have a bright fringe there. So if we're going to set up this problem, the extra path difference between ray 1 and ray 2 will be equal to 2t, because they'll go up and down, plus the net phase inversion. However, the net phase inversion is 0 because these are both undergo phase shifts of 180 degrees, so there is no relative difference between them. Now, since we want constructive interference here, then we're going to set that extra path difference to m lambda. Now, this lambda is not lambda 0, but this is lambda that is within the film. Now remember, the film in this particular case is where the extra path difference is taking place. So that's in here, which is within grease. So we're going to need to solve for lambda sub n. Lambda sub n is lambda in a vacuum divided by the index refraction within the medium that it is taking the extra path. So this is 500 nanometers divided by the index refraction within silicone grease, because that's where this film is. So that's 1.5. And so our lambda sub m in the film is 333 nanometers roughly. So now we're going to go about to try to solve for this spacing distance of x. And once again, we look at similar triangles. We look at this little triangle in here. You can see x and t, this height here, and this length along here. And then if you look at the total length L, and this h here, this distance that it's been propped up by that piece of paper. And so we can again write a similar triangle for that. We can write x is to t as is L is to h. And we're going to replace t with this expression, where t is equal to m lambda sub n divided by 2. So we have x is to, and then replace that in, And if we're going to solve for x, we would have the following expression. M lambda sub n times L divided by 2h. And so we're now ready to sub in our numbers. Our wavelength is 333 nanometers. That's within the film. The length of the plates is 0.1 meters. Oh, we need to change this into nanometers, so let me modify that. I keep on forgetting to do that. Then divide by 2 times h, which is 0.02 millimeters, so that's 10 to the power negative 3 meters. And so you will get x equals m times 8.33 to the power of negative 4 meters, or that's x equals m times 0.833 millimeters. So that means that these fringes are going to be 0.833 millimeters apart. That's the bright fringes, or the dark fringes in that case as well. Okay, and that's it for example number 6. And I should just add just a few little observations. If you look at this formula right here, you can see that x is proportional to the wavelength. And so we started with a wavelength of 500 nanometers in the last two examples. And if we had changed to a different wavelength, say we use something like red with a longer wavelength, so that if lambda was longer, say for like you were using something like red instead of violet or blue, then the spacing between these fringes would get spread out. So larger wavelengths will cause the fringes to spread further apart from one another. And of course, the thickness T affects things as well. And so there's a lot of different variables. And that's it for this example.